This video is about multiplying and dividing complex numbers. So if I have two complex numbers, z1 is equal to r1 e to the I theta 1, and z2 is equal to r2 e to the I theta 2, then multiplying these two complex numbers together, I can say that I have z1 times z2. Now obviously the order in which I multiply these is not important, so I could write this as r1 times r2 then adding the powers together, I'll get this, or factorising the I outside, that. So multiplying these two complex numbers together gives this result. Or if I was dividing, I could write that as r1 divided by r2, and then taking away the powers, and then again factorising out the I, like that. So we have these results, which should hopefully actually make sense when you think about what we learned about the modulus and the argument last year in year 12. Oops. So basically what we're doing here is we're multiplying the modulus or moduli together and then adding the powers if we are multiplying our two complex numbers together. Or if we're dividing, then we're going to divide the moduli and we're going to subtract the powers. So that makes sense. We saw that in year 12, that if I multiply two numbers together and then look at the modulus of that, that's just going to be the same thing as the modulus of the first number times the modulus of the second number. The argument of two complex numbers being multiplied together is just the sum of the two arguments. Similarly, we also saw that when you divide two complex numbers, the modulus of that is equal to the modulus of the first one divided by the modulus of the second one. And then if you're looking at the arguments, then the argument of the two complex numbers being divided is equal to taking the two arguments away. We saw all of these results last year, so it should make sense then, these results that we've just seen. So let's have a look at a few examples using those. So we've got our two complex numbers here. We've got our 2e to the pi I over 6 multiplied by roots 3e to the pi I over 3. And we want to write it in x plus iy form. So I'm just simply going to multiply the two moduli together. So 2 times root 3 will just be 2 root 3. And then I'm going to add the two arguments together. So I'm going to do pi over 6. I don't need to include the I here. So I'm just going to do pi over 6 plus pi over 3, which is pi over 6 plus 2 pi over 6, which is 3 pi over 6, or pi over 2. So my argument of the new number is pi over 2. Therefore, then I can say that I've got my modulus, which is 2 root 3, e to the I pi over 2, which I can write as being 2 root 3 cos pi over 2 plus I sine pi over 2 cos pi over 2 is 0, sine pi over 2 is 1, so I just get 2 root 3 I. And that is my complex number. That is the result of multiplying these two numbers together. So I multiplied the two moduli, I added the two arguments, and then put those results together to get the result that I wanted. Next, I want to express two lots of cos pi over 12 plus I sine pi over 12 divided by root 2 cos 5 pi over 6 plus I sine 5 pi over 6. And I want to write that in exponential form. So first thing I'm going to do, I can rewrite the numerator as being 2e to the I pi over 12. And the denominator as being root 2e to the I 5 pi over 6. So that's just me rewriting both of those in exponential form. I can do the 2 divided by the root 2. That's me dividing the moduluses. And now I'm going to subtract the arguments. So I'll have pi over 12 minus 5 pi over 6. The 2 over root 2 will simplify. If I rationalise that, will just be root 2. And then if I do the pi over 12 plus the, so the pi over 12 minus the 5 pi over 6 will give me minus 3 pi over 4. And that is my answer. Final example for this video, slightly more complicated one, or certainly written in a slightly different way. We are told that z is equal to 2 plus 2i. I am told that the imaginary part of z times w is 0. I am also told that when I take the modulus of zw, that's going to be equal to 3 times the modulus of z. I am told to use geometrical reasoning to find two possibilities for the complex number w, giving my answers in exponential form. So I know about z. I don't know about w, that's what I need to find out. But I am given some information about the product of zw. I'm told that the imaginary part of the product is 0, and I'm told that when I multiply the two moduli together, I'm going to get 3 modulus of z. So, the modulus of z, let's work that out, because I know that z is equal to 2 plus 2i. So therefore, the modulus of that is going to be 2 squared plus 2 squared square rooted. So that's going to give me 2 root 2. Now, I also know, I can also work out the argument of z as well. Let's do that by doing tan inverse of 2 over 2, which is going to give me pi over 4. So that's the argument of z. Now, I was told that the modulus of zw is equal to 3 times the modulus of z. Now, I know that the modulus of zw could be written as the modulus of z times the modulus of w. Which means, therefore, that the modulus of w is going to be 3. So I know that r equals 3 for w. I am also told that the imaginary part of zw is equal to 0. So that would mean that on the Argand diagram, if the imaginary part is 0, then it would have to be on the real axis, either here or here somewhere. Which means that the argument of this result, the argument of ZW, would have to either equal 0 if it was here, or pi if it was over here. Now, the argument of two complex numbers when they are being multiplied together would be equal to the argument of one of them plus the argument of the other one. That's going to equal 0 or pi. The argument of z, I know that that's pi over 4. I worked that out previously. The argument of w, I don't know that yet, but I know this is going to either equal 0 or pi. Well, if it equals 0, then theta would have to be minus pi over 4. The argument of w would have to be minus pi over 4. Or, if it equaled pi, theta would have to equal 3 pi over 4. So these are the two possibilities for the argument of w. So I know that the modulus of w is 3, and I've got the two different possibilities for the argument. So I can say then that w is going to equal either 3e to the minus I pi over 4, or, oops, sorry, that should be a 3, not a R then. 3e to the I 3 pi over 4. These are the two possibilities for w. So in this case, I was just using the fact that I can split the modulus of the product of ZW into the modulus of Z times the modulus of W. And I was using the fact that I can split the argument of ZW into the argument of Z plus the argument of W. I'm just using those results to help me to solve this problem.